So today we have one of our own PhD students, Jordan van Beeck. And meanwhile, he's already a fourth-year PhD student in the team of Connie Art. So he's an astroseismology expert, and his thesis topic is what you see there. So you see about gravito-inertial mode coupling, and that was also his talk of today. And he promised me to explain it in a very easy and smooth way.
Yes. So, hello everyone, and welcome to my seminar on nonlinear gravito-inertial mode coupling in SPB stars, work done in collaboration with Dominic Bowman, Tim van Holst, Connie Art, and Jim Fuller from Caltech. And as promised, I'll first try to give you a more better understanding of some of the words in this title. So I'll start with the question, what are SPB stars and gravito-inertial modes? Now, slowly pulsating B stars are pulsating stars, as the name gives away, and you can therefore locate them on the astroseismic HR diagram, or the pulsating star Hertzsprung-Russell diagram, and I've done so here on the left of the figure, on the right of the screen, I mean. Where the luminosity is on the y-axis and temperature on the x-axis. These stars are multi-periodic in the sense that they display multiple modes at the same time, and they have gravito-inertial modes, which are modes that are restored by both buoyancy and the Coriolis force. And since the Coriolis force is inherently related to the rotation rate of the stars, it's very important to take into account these rotation rates when analyzing these stars. They have masses ranging from 3 to 9 solar masses, and their pulsations, so these gravito-inertial modes that we observe, typically have periods ranging from a half a day to approximately 5 days. These modes are low degree and high radial order, meaning that there are few nodes on the surface, as you can see in this specific representation here. There's only one node at the surface. And high radial order, meaning that there are many nodes inside the star in the radial direction. The rotation rates for these stars vary wildly. They have rotations going from near critical to all the way to 1% of the critical rotation rate, as was found by a study by Maegede Pedersen et al. In 2021. And their internal energy transport is very approximately given by the following structure. You have a convective core, and you have a radiative envelope in which your gravito-inertial modes propagate. Now, how are these modes excited? Well, that is classically or linearly, they are linearly excited through the classical Kappa mechanism, which is basically a heat engine, where your heat is added to the system due to compression of partial ionization zones inside your star. And for the SPB stars, these partial ionization zones are the iron group opacity enhancement in your radiative envelope at a temperature of almost 200 kilokelvin, also called the Z bump. So now that we have a better understanding of what these SPB stars are and what modes are propagating inside them, we should ask ourselves the question, why do we even care about nonlinear mode coupling, right? So in order to give you a better understanding of why we care about nonlinear mode coupling, we first take a look at what was achieved already with linear astroseismology for these types of stars. Linear astroseismology, or the astroseismology, what typically astroseismologists talk about in these talks, uses frequencies to probe the internal rotation profile of an SPB star. It uses frequencies to probe and period spacing patterns to probe the internal mixing profiles of these stars. If you delve into the non-adiabatic linear asteroseismic theory, you can get an idea of which modes are excited or should be excited and which modes are not excited. And you can even use you can even theoretically simulate what the effect is of internal magnetic fields on these frequencies and use that to infer observationally how such internal magnetic fields should look like and what their structure should be. On the other hand, nonlinear asteroseismology should also account for the way amplitudes are limited through excitation of specific combination modes. And it should import some nonlinear frequency shifts. Notice there's a big difference between the two, in the sense that linear asteroseismology uses only frequencies to probe these internal rotation profiles. There's no inherent amplitude information from the linear theory, and thus no inherent information on the amplitudes of the modes from linear asteroseismic modeling. Whereas nonlinear asteroseismology can give you some idea of these amplitudes through this excitation of specific combination modes, which we observe in typical frequency spectra. And they do that by means of transferring energy between each other, and this is also known as nonlinear mode coupling. So that's the premise of nonlinear asteroseismology and nonlinear mode coupling. Let us have a look at some observational perspectives on whether or not we can actually find hints that this nonlinear mode coupling is actually happening or not. And to do that, we look at a specific sample of SPB stars, a quite large sample of 38 SPBs observed by Kepler, which are situated on an HR diagram in this figure, where they have widely varying masses that span the entire SPB mass grid, so from 3 solar masses all the way up to 8 solar masses. You have you only have a few binaries in there and many single stars. And what is also interesting in this figure is that there was this figure was taken from Pedersen et al. That there is information on the so-called instability strip for the modes in these SPB stars, in the sense that this color coding gives you an idea of how many modes should be excited, how many dipole and quadrupole modes should be excited inside these stars according to adiabatic linear theory. These, as I mentioned before, the rotation rates for these SPB stars can vary wildly, and this is shown in this figure where the important information is on the y-axis. This is the rotation rate in terms of the critical rotation rate. And then you can see that there are several stars that have rotation rates that are very close to zero or statistically insignificant from zero, whereas others are very close to breakup speeds. So how do we go about in them extracting information that is of relevance for nonlinear to simulate nonlinear mode coupling? Well, we first go through the variability analysis cycle that we go through when we also perform linear asteroseismology, and namely we do a iterative pre-widening analysis where you take your light curve that you first correct for characteristics and you make sure that there are no systematic signals left in there, as we all do, and then analyze that by putting that through a Fourier analysis module of your choice. Using the Fourier analyzed data, you then select the most significant signal according to a signal selection criterion of your choice. Then you make a model of that, and typically what we do is we make a sum of signs model where you put the extracted amplitude information, the frequency information, and the phase information from your Fourier analysis selected signal into your least squares model. You fit that model to your light curve, obtain the residuals, do Fourier analysis on the residuals, etc. And you do this in an iterative way until your signal selection criterion says, well, the next signal we're trying to extract is insignificant. And then you obtain your final light curve model. An example of what such a Fourier analyzed spectrum looks like is the following for an SPB star, where these points, these lines in gray are basically your Loomis-Cargo periodogram, one of the frequency analysis, the Fourier analysis techniques that we typically use, of your entire light curve, so that you have multiple modes that seem to be grouped. And then you also have an indication of what is left in the final residuals of your light curve model in orange. On the y-axis, we have our amplitudes that we can then extract from our model, and then this is the frequency axis. So in linear asteroseismology, we would only use these frequencies. And these amplitudes and these phases are byproducts of our analysis. Now, when we do that, there is a certain degree of there's a certain arbitrary, there's a choice that we need to make, right? We choose which Fourier analysis technique to use, we choose which signal selection criterion to use, we choose when to stop our iterative pre-widening, we choose what to use, how we fit these least, how we perform these least squares fitting, and therefore, from Beeck 2021, we check the self-consistency of this iterative pre-widening procedure by varying the strategy. And by that I mean that the way we fit, by that I mean varying the way we perform the fitting, the least squares fitting, and the way we determine signal significance. And we therefore developed 5 strategies, and then we wanted to compare these strategies to see whether or not these light curve models that we obtained from these 5 strategies are internally consistent or not. And to do that, we determined a specific metric, the fraction of variance explained, that is scaled to the number of timestamps in your light curve and the number of parameters in your model, which is conveniently called FSV, and which I will call FSV from now on. And computing this metric for these, after you've run these 5 iterative pre-widening strategies on all of the stars in our sample, we then found that approximately half of our stars have a FSV value that is more than 90%, meaning that there's approximately more than 90% of variance in our light curve that can be explained by our sum of science models. Here you have that information per specific strategy, and these high FSV stars are stars for which this FSV value is more than 90%. We also found that there's a bunch of stars that have very close, that have closely spaced frequency groups. So that means that our analysis will leave residual signals in there that can, that reduce this FSV value, so that your sum of science model does not become a great way to analyze this star, and then this of course means that your FSV values are lower, and that you would not maybe rather use a different technique or different model to analyze these stars. And finally, we also have a notorious category of outbursting stars, where the FSV values are very low. And because we have significant non-sinusoidal outbursts of amplitude in these light curves of these stars, which are not explained by our sum of science models, obviously. So the category which we're going to focus on today are these high FSV stars. And why do we do that? Well, we want to actually extract information on what are called so-called quadratically locked modes. And those are modes sum frequency triads that need to fulfill the following relations. Basically, we want that modes alpha, beta, and gamma have frequencies whose difference, taken the specific way, is approximately 0 cycles per day, or resonant. And then their phase differences should also account to some specific integer multiple of pi over 2. Moreover, we want them to be locked because we see that the stability of these, these amplitudes that we extract from these sum of science models should not vary much over time. In principle, they should even not vary over time. So this is another criterion that we need to impart, and that is typically satisfied for the modes or the signals that we are analyzing as well. And together, we can then, if these three criteria are fulfilled, we get a quadratically locked triad or a quadratically locked modes. Why do we care about that? Well, if you look at this specific frequency relation, you can see that if you have one mode in this frequency group and two modes in this frequency group whose sum is approximately that of this a mode in this frequency group, we can have some sort of quadratically locked mode triad with modes from this frequency group and one from this frequency group. So in principle, if you have quadratically locked modes, you can start to explain why there is this specific frequency grouping phenomenon. When we look for these numbers of quadratically locked mode triads, we find that there are approximately, that there are triads that fulfill these conditions, and that for high FSV stars that there are at least 2 to 8, typically 2 to 8 of these candidate resonances per star. Hence, these resonant couplings, or these quadratically locked modes, seem to be ubiquitous among the modes that we analyze from these SPB stars. So, after having determined that these resonant couplings are ubiquitous, what can we do with them? For that, we need to have a look at the theory more into depth. And before I go and delve into the nonlinear astroseismic theory, I first want to explain to you how we model gravito-inertial modes in linear astroseismology, and more specifically look at their equations of motion, which look like this, where you have your driving term. This is where your kappa mechanism drives your mode. Then you have your Coriolis force term and your pressure and buoyancy term. Now, in order to derive these equations of motion, you have to make certain assumptions, and the main assumptions that we make here is that our star is uniformly rotating and not centrifugally deformed. And in order to take into account of the Coriolis force, using the typical angular parts of your eigen vectors, the spherical harmonics, one would need to compute sums of infinite numbers of these spherical harmonics, because the separation of variables becomes impossible. However, one way of avoiding having to compute these sums of infinite terms of spherical harmonics, we use the traditional approximation for rotation, where we neglect the horizontal component of your angular frequency vector for rotation. And this then renders this separation of variables possible again, and then we can compute the angular parts of our eigenmodes using the Laplace tidal equations. Now, when we move from the linear equations of motion to the nonlinear equations of motion, we call them coupled mode equations. And we have these interactions between these terms that that can be modeled as some sort of nonlinear acceleration term in your equation of motion, which is here at the quadratic level shown as this term. If we then also expand the displacements, these are the displacements caused by your modes, or rather the Lagrangian displacement in your star. The individual displacement caused by your modes are these. If we then expand the Lagrangian displacement in of your star into these linear eigenmodes, we have a factor appearing in our expansion that is the amplitude of our specific mode. So this is where your amplitudes come in. And if you then also take into account orthogonality, you can derive a specific form of coupled mode equations, the extended coupled mode equations, which then would take into account the interactions of one of your modes with all other modes in your star. Now, we've moved from computing sums of now, in order to do that, you need to compute sums of specific mode interactions between an infinite number of possible modes in your star, because these modes in these coupled mode equations not only take into account the visible modes, but also those modes that have amplitudes that are too low to be observed. And that means that you're again dealt a bad hand. So in order to simplify that analysis, we have to make one more assumption, and that is that we're dealing with isolated some frequency coupling, in the sense that the interactions between the modes in your some frequency resonance are strong enough that the interaction that they're much stronger than the interactions with all other modes, in the sense that we can neglect these interactions with all the other modes. And if we do that, well, so this is our some frequency that we're considering. If we do that, we can then derive the nice amplitude equations, of which an example is shown here. And these amplitude equations basically show how your amplitude, so this is a derivative with respect to time, change over time according to the interactions with two other modes. So here we have mode A, B, and C, and the amplitude of mode A changes due to a specific first term, which takes into account the linear growth rate, or basically this says, if we neglect this term for now, this says whether or not in the linear adiabatic approximation your mode is excited or not. If gamma is positive, your mode is excited. If it is negative, it is damped. And therefore, you can also see why in the linear approximation you can not gain any information on the specific amplitudes that are to be attained, because this, well, for one, this term is not there. And if gamma is positive, well, good, your mode is excited, but it will increase in amplitude indefinitely. If it's negative, it will just damp until it hits an amplitude of 0. So in the linear approximation, we cannot have any information on your amplitudes. So enter the nonlinear first quadratic approximation. Well, then we have a term that can counteract this linear effect, and then we have a specific coupling coefficient that gives a measure of how efficient energy is shared between these modes, or how efficient the energy is transferred between the modes, and then we can use that to get some more information on how amplitudes are limited. So in order to compute these coupling coefficients, I developed a code, the AE solver, that uses MESA models and gyre, MESA stellar revolution models and gyre pulsation models to compute specifically these coupling coefficients, and then use those coupling coefficients to then get information on the amplitudes that one can attain according to the nonlinear coupling in isolated resonant mode triads. If we use that to compute this coupling coefficient for a specific mode triad, for which the spherical degree of your specific parent mode is 2, and your azimuthal order is also 2, and then for the 2 other modes 1, and the spherical degree is 1, and the azimuthal order is 1. Inside of a nice polytrope, which has a mass of 3 solar masses and 4.5 solar radii, and which is a fair approximation at the first level of the internal structure of a SPB star, we get some values of approximately 10 to the 9th for these coupling coefficients. However, when we do that for a near terminal age main sequence for solar mass slowly pulsating B star model using MESA plus gyre that is rotating at 20% critical, we get coupling coefficients that are a bit lower, and that's because using these MESA plus gyre models, we have a specific near core zone that is very important and the looks, well, the internal structure there looks quite different from your polytrope. And this is exactly this zone that actually sets the value of that primarily determines the value of this coupling coefficient. And these values are in accordance with what one could call one of the seminal works on this topic, the Lee and 2012 paper. So we have these amplitude equations. How do you now compare the results that one might obtain from these amplitude equations with what we have in observations? Well, one of the things we didn't, one of the things we still need to impart on our solutions is that the amplitudes do not change over time. That is, we search for stationary solutions of this set of amplitude equations. So you not only have an amplitude equation that determines the evolution of your A mode, but also for the amplitude of your B and C mode, and also of your specific phase term here. So when you set these to 0, you can then analytically derive a form for determining the amplitude of these specific modes for a specific case of stationary solutions. And when you then compute the ratios between these stationary amplitudes, you have something that is determined solely from linear astroseismic, linear parameters, namely the linear driving rates and the frequencies. And it's exactly these ratios that are very important in determining whether or not our models seem to are reminiscent of what is happening inside our star, because these are readily obtainable from our sum of science models. Now, typically such quadratic ratios are 10 to the unity and 10 to the -2 for our TAMS models. But what is important, what is quite intriguing, is that there are no nonlinear terms present in these stationary amplitude ratios. So why do we compute these coupling coefficients, right? Why aren't we satisfied with just using linear non-adiabatic theory to just compute these ratios? Well, in order to answer that question, let me ask another question. When do we have stable stationary solutions? And by stable stationary solutions, I mean, let's say your system has attained your stationary solution. What happens if we then perturb it outside of that stationary solution? Does it return to the stationary solution or not? This happens to be very dependent on the type of mode triad that we're considering. And we have three types that are of importance. The first one is where mode alpha is linearly damped, and mode beta and gamma are linearly excited. This is the direct resonance case. The second one is where the alpha mode is linearly excited, and these are linearly damped. That's the parametric resonance case. And then we have a third case where all three modes are linearly excited. Turns out, if you do the math, that this one is always unstable. And for three different modes, this one is also, is always the stationary solutions of this one are always unstable. This one is also always unstable if you have three different modes. And only for the parametric resonance case can we find stable stationary solutions. So if we numerically integrate the amplitude equations, and we can show you an example of such a stable stationary solution, where you have initial amplitudes that start all the way down here for your two damped modes, and one linearly excited mode that starts to increase in amplitude, and at a certain point, boom, here we have energy transfer between the modes, and we attain the stationary solutions and stay there for an indefinite amount of time. But you can also have this depending on your input parameters. So this is a widely varying amplitude solution. It's also called the limit cycle of your amplitude equations. And these are not the modes we're looking for. These modes is what we're looking for if we want to compare with our quadratically locked quadratically locked modes determined from observations. So how do we do this? How do we determine this mathematically? Well, we first realize that our amplitude equation is no more than an autonomous dynamical system, and that their stationary solutions of these amplitude equations are no more than the fixed points of this dynamical system, and that the stability of these stationary solutions is no more than the stability of these fixed points. Then we have to determine what the stability of the fixed points is, of course. And to do that, we rely upon one of the big theorems in dynamical system theory, the Hartman-Grobman theorem, which says that if your fixed point is hyperbolic, then you can determine the stability of your fixed point from a linearization around your fixed point. When is your fixed point hyperbolic? Well, if the Jacobian matrix of your dynamical system, it has eigenvalues that are non-zero, and if the Jacobian of your dynamical system is also non-zero. So we call this the hyperbolistic condition, and this is the first condition that you need to fulfill if you want stable stationary solutions for your amplitude equations. Now, turns out, well, not unsurprisingly, that this condition is really dependent on your coupling coefficient. So there's one reason why we compute our coupling coefficient. Then, when we then look at our linearization, well, we can also have, then we need to impart some other conditions in order for these perturbations around your fixed point to be stable. And the first one is this triad agnostic condition, where we have that the sum of your linear driving rates of your in your mode triads should be smaller than 0. And then we also have your triad-specific condition, which is very much dependent on triad type, as I explained earlier. And it is also very much dependent on the values of your linear driving rates, their sum, and the frequency difference. I'm going to refrain from giving you the exact expression here, but I'll show you some pictures of what the stability domains are according to this condition. These two conditions, in fact. So in order to do that, we introduce some dimensionless parameters. We have θ2, which is basically a ratio of your driving, or of your damping rate, in fact, for gamma B, for mode B, and your driving rate for mode A, and the same for θ3. And then you can compute these stability domains for specific values of this delta omega, so your frequency difference over your sum of your driving rates. And the areas that are given in black over here are regions of the parameter space in which you have stable stationary solutions. So we have that for these three values. We can also get that for these three values. And note that the values on this axis, on these axes, change quite rapidly. Go from 10 up all the way up to 2,000 if you increase that single parameter here. Now, what is the range of parameters we have in our specific SPB models? For this NearTamps reference model that I've been using during this presentation, this value is about 10 to the third. And the values of these, theta, this should be 2, 3, is about 10 to less than 100, actually. So we're in this region. We're quite stable. Hence, for the computed mode triads that we for the mode triads that we compute, we have loads of possible combinations or possible mode triads that can give rise to stable stationary solutions that can then be modeled using non-universal cosmology. You can also ask a different question, and that will give you a different reason why we compute mode coupling coefficients. Namely, when does this mode energy transfer start? When does the mode coupling start? And in order to analyze that, we can make an approximation that during the initial phase of mode transfer, mode energy transfer, the amplitude of the parent mode stays constant. And if you do that, you can derive an amplitude, AT, that needs to be attained by your parent mode before your energy transfer starts. And again, of course, our mode coupling coefficient is very important in determining this instability amplitude. So if you want to know if your observed mode triad could have even started the mode energy transfer, you need to compute the amplitude, you need to compute this instability amplitude, and you need to make sure that the amplitude that your mode has now is larger than that instability amplitude. So these are theoretical amplitudes. How do we then compare that with observed amplitudes? We have to use some sort of disk averaging, because the signal that we obtain with our telescopes is of course disk averaged, and it's also a luminosity fluctuation. It's not necessarily an inherent amplitude of our waves. And there's a nice formalism here in Fuller 2017, which I'm also not going to explain right now. But if you do the disk averaging properly, and you account for if you account for the factors that you need to account for, then you get disk average luminosity fluctuations that are on the order of 10 to the minus 4 to 10 to the minus 7, which is again in accordance with the values that we have for our seminal reference work. Now, what can we conclude from this? That is that, according to our observations, these resonant couplings that we detect seem to be, well, ubiquitous among these quadratically locked modes seem to be ubiquitous among the detected SPBG modes. Yet we need to take into account that we are certain that our light curve models are inherently consistent with each other if we vary in pre-widening strategy. So we need to check the error budget of our pre-widening strategy. From theoretical perspectives, we found that isolated three-wave coupling theory plus MESA and gyre models can produce parameter values that are first in accordance with literature, and second, can have stationary luminosity fluctuations that can be compared with observations. But in order to do that, if you want to compare with these quadratically locked modes that you can observe and that seem to be ubiquitous among these G modes, you need to also take into account the stability of these stationary solutions and when the energy transfer starts, or the onset of instability. In the future, this can then be used to do astroseismic nonlinear modeling of these Kepler SPB resonances. Well, of these resonances of SPBs measured by Kepler. And that can also be used for SPBs that are observed by other long baseline telescopes, such as Plato. But a more elegant way of stating this outlook is by Zhong et al., who in a review on this nonlinear astroseismic field by stating that the time of renaissance for nonlinear astroseismology now has come. And with that, I think I am finished.
Thank you, Jordan. Are there any questions or comments or feedback?
Hi, Jordan. So you found mode coupling factors of 10 to the 9th for your polytrope model, right? And then when you showed an actual stellar structure model, it changed by a few orders of magnitudes. So I assume that the largest change in this coupling factor is because you now have an actual stellar structure model. On the other hand, you also changed the mass slightly of your star. I assume that this doesn't change the things very much.
No, not. Well, it might change it by a factor of 10 or 100, but not 10 to the 4th or 10 to the 5th.
Yeah, and the fact that you have rotation in your actual stellar structure model, does it also change it by quite a bit, or is the
well, we don't have rotation in the actual stellar structure model. We only have rotation in the gyre model.
In your gyre model, yes. But does that have an effect as well, or not really?
it should have an effect. But if I recall correctly, I also imported this. Well, I also computed the modes in this polytrope using the traditional approximation for rotation. So I don't think it's that. Well, I don't think that's where the big difference comes from.
Well, I didn't expect it to be the big difference, but I was just curious if there was a small difference due to these things as well, or
yeah.
not really.
Well, definitely due to the mass difference. I don't think there's a big difference due to the rotation.
Okay, thanks.
Hi, Jordan. Nice presentation. So since the time of Renaissance has come, when can we expect our observational amplitudes to inform us about our stars?
As soon as possible. Yeah, depends on the modeling efforts that will take place in the next couple of months.
Hey, so in the beginning, you mentioned that one of the core assumption is that the mode cavity is spherical, right? When you analyze these things.
Yes.
But I'm sure you're well aware that especially you have a lot of highly rotating stars, this is not the case.
Yes.
Right? They're like
Correct.
5 to 10% larger than their spherical counterparts. Does this immediately take this off the board, or can you deal with that, or?
We currently do not have any theory to deal with that. But yeah, I mean, the current theory is, so we're using the traditional approximation for rotation should be okay up to, let's say 60% critical rotation. Yeah, so the findings from our studies should be okay up to 60% critical rotation, and then afterwards, well, it really depends on how much your mode cavity is deformed, and I can't say too much more about that right now. It's would be very interesting to develop future theory that can take that into account.
Hi, Jordan.
Hi.
Thanks for the nice talk. I will have a few questions.
Sure.
And, maybe a bit simpler questions. It's gonna take you, I don't know, not that much time. Can you get us back to slide 20, please? Yeah.
Here we go.
So it seems that the orange color there shows the net result, right? So after
that's the residual.
So it seems
pre-diagram.
that with your model that you show there, you're not able to explain the black curve properly. What's wrong with your model? Did you consider some other model?
Well, during the iterative pre-widening procedure, during the signal selection procedure, actually, we take into account that when we extract a signal, we make sure that we don't extract the signal in the vicinity of your that. Well, we don't extract a future signal in the vicinity of that signal, because that would affect the frequency of your that would affect the stability of your light curve model, in the sense that you would have correlated frequencies in your light curve model. So what we do is put an exclusion zone around your every time you extract a new frequency, and search for frequencies that are not in these exclusion. Well, search for new frequencies that are not in these exclusion zones.
Could it be that sinusoid is not a good?
Yeah, so it's probably a non-sinusoidal signal as well. Yeah, so that would mean that you might have a frequency that is not that is varying over time, And then this would also cause some of these features in these periodograms. And that is also interesting because then you can, in principle, numerically integrate these well, if that is the case, then we'd also have a change in your phases, because they're correlated, and you can perform a numerical integration of your amplitude equations and can look for a varying phase that matches that time varying phase from your observations.
Yeah, and maybe a second question, a more general one. So when I talk to people at conferences, they disagree on many things, but agree on one, that astroseismology became a thing in the past decade. No? And you show that nicely, I think, in one of your slides, that by just exploiting frequencies, we learned about interior rotation, internal magnetic fields, and blah, 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 and we know that, you know, all those advances together were awarded the Kavli Prize, right? Why the hell do you need amplitudes? Stick to frequencies.
Well, why do we need amplitudes? We can use that to get even better constraints on well, physics in your internal structure models.
What kind of
Well, so what is it? So you can use that to, what's it called? Well, to get more information, for example, on I think angular momentum transport, but I have to double check that.
That was it? Or? Okay, well.
Yes.
Any more questions?
First, a remark to Matthias with 2 T's. There's a synergy grant vacancy open to investigate what you are asking, so don't blame Jordan, please, for the moment. Jordan, a question for you. Now, with all this knowledge that you didn't have at the Van Beeck et al. 2021 paper, right? If you go back to your 38 stars, you had made a ranking of promising candidates.
Mm-hmm.
Can you go back to that ranking, and would it change or would it stay the same?
That's a good question. I think.
What would you do to revisit it?
Well, first of all, compute these amplitude ratios that we didn't compute back then, and based on that, I don't think there will be many difference actually. What we did compute when we did Van Beeck et al. 2021 in our go back to, where's my amplitude ratio? Are different ratios where we compute basically the amplitude of your, well, the ratio of the amplitude of mode A divided by B and C, the amplitudes of mode B and C, because that was a specific factor that was given in literature back then. But after having done the math, it would more definitely be interesting to have these kinds of factors, all the more because each of these modes has a specific correction factor due to this disk integration for your luminosity that is approximately the same, so it should approximately cancel out. So these factors should approximately be the actual amplitude ratios that we observe as well. Whereas if you would have that other ratio, there's one factor on top and the factor squared below, so you would be dependent on your disk integrated luminosity. And also the normalization of the modes that you use in determining your coupling coefficient. So Yeah, the main thing I would do is compute these ratios, actually.
Yeah, so I have a very naive question about the amplitude equation.
Yes. Which one? This one?
Yeah, that one. So it's about so I was a bit puzzled by the fact that you take the absolute value of the coupling parameter, which I can maybe understand, but then I should understand what the phase parameter is, and I don't. So it's the phase between what and what? Can you comment?
Okay, so this is some sort of relative phase parameter in the sense that it's consisting of the difference. Well, maybe I should write it down. So epsilon is difference between the frequencies, oops, times the time, plus, if I recall correctly, this is the phase of A minus the phase of B minus the phase of C plus delta, and this delta that comes from your coupling coefficient, which is defined as so this is a complex coupling coefficient, and the coupling coefficients that are used is basically the absolute value of your, or your modulus of your complex mode coupling coefficient, and this, oh no, this should be delta, of course. Oops. This is basically the phase of your mode coupling coefficient. But since we are using the approximation that we are only using adiabatic modes, this phase coupling coefficient, phase of the coupling coefficient is 0. So this is not important for the rest of the work. But this is basically your phase difference between the modes. And then you have an extra phase factor due to your frequency difference. Does that answer your question?
Okay, I suggest we thank Jordan again. Thank you very much.